So we are going to be looking at sampling distributions again. It's chapter 9. And sampling distribution B deals with the difference in two samples. It's not that uncommon that when you're collecting data, you're not just collecting it on one group of people, right, one population, but you might be collecting the same kind of question for two distinctly different groups. So for instance, you might ask a question like, are you going to vote Republican in the governor's election? And your population consists of two distinct groups, females and say males. And so P1 can be the population, right, of males, and in particular, the percentage are going to vote Republican. P2 is the population of females, that's where you're getting your data from, and it's going to be percentage of who vote Republican. And so what you're interested in is there a difference between the two? Right? And we're not so much interested if 20% are going to vote Republican or 99% are going to vote Republican in either group. What we're interested in is there a difference between them? So what we tend to calculate is P1 take away P2. Would you agree that would tell you the difference between them? Now, if that was 0, wouldn't that mean that women and males, women and men, whatever you want to phrase it, self-identified males and self-identified females, that they vote the same way, whether that's they vote a lot of Republican or they hardly ever vote Republican, but they vote the same way? Or that's what you'd get if the answer was 0. But if you got other answers, wouldn't you be able to have some information about the differences between the two groups? So for instance, if that number is 0, they vote the same way. Suppose P1 take away P2 was positive. Suppose it was bigger than 0. What would that be telling you? Suppose the difference was, 10%, 0.1, for instance. What would that be telling you?
A larger proportion of men vote Republican than women.
Right. Men more than women. What you said is right. Vote Republican. Would you agree that if it was the other way around, in other words, the difference was negative, then men are less likely than women to vote Republican? Does that kind of make sense? So we're really after which one of these three is going on. And even if we could put a number on it, would be really good. So if this number was 0.1, we could say 10% more men are likely to vote Republican than women, or 5% less men than women, right? The difference between them. And politicians are always very interested in these kind of differences. So they might say, a lot of women tend to vote for this guy, less and less men. So he would be saying to himself, well, okay, I've got to figure out if I want to get more votes, how I'm going to be attractive to the men vote, right? What kind of things are they interested in? And I'll be interested and like those things as well. That type of, what most politicians do is that they are very flexible in a lot of their views, depending on how many votes they get or lose, depending on it. Would you agree? That most of them, so how do they know what are good and bad? Well, they do analysis like this and they say, yeah, if I'm going to piss off one group, shouldn't you piss off the one that has the less votes? Right? So if you're in a state and gun rights are very strong, you probably want to be in favor of guns if you want to get elected, right? If you're in an area that is anti-abortion, you probably want to be an anti-abortionist then if you can get away with it, right? Because that's likely to get you more votes. So let's do a less serious example. And we're going to have two pretend groups. And P1 is going to be a sample. And P1, we asked young people. And young can be described in any way you like, but anybody from babies to 30-year-olds are young. And then the other group's going to be called the old, and the olds are 30 pluses. Now, I'm just making that up, right? You can decide yourself what old and young is. But we asked them, do they like Pepsi as their favorite drink? And the young ones, it was 0.4. And in the old group, it was 0.45. And in this group, we had a sample of 300. And in this group, we only had a sample of 200. And so what we're going to calculate now are some of the numbers that you need to do this analysis. The first one is the difference between the two. Would you agree that's probably the easiest calculation to do? Because don't you just take whatever the first one is and take about the second, right? So in this case, the difference happens to be a negative 5%. Are you comfortable with the negative? Superficially then, does it look like young people like Pepsi less than older folk? Not that they don't like it, but they like it less often, right? You could turn it on its head and say old folk like Pepsi more than young folk, right? But I'm doing it from P1's perspective. So less young folk compared to old. Now, there's a second guy that we need to analyze this, and it's called the standard error. Remember that guy with the square root formula that we used when it was one sample? We're going to use that same thing here. And it's a quite ugly formula. I'm not disguising it. It's just downright ugly. You agree it's a pretty messy looking formula. If you look at it carefully, isn't it just the guy that you would use last Friday? Isn't that for a single proportion? And isn't that the single proportion? And haven't you just added them together inside a big square root? So it's not that the formula is that different looking, isn't it just the same guy twice? So to calculate that is going to be very messy, but we still need to do it. So it's going to be the square root of, let's do the P1s, 0.4. One takeaway P1 is 0.6, and the sample size is 300, plus P2 now, 0.45. One takeaway that gets you 0.55 and divided by 200. So you're going to get questions where they just ask you to find P1 takeaway P2 and the standard error, right? And that's it, right? And then later on, we'll do more of this. Now, you really do need a calculator for this fella. And I'll start with the square root. It's going to be 0.4 times 0.6 divided by 300. Okay, that's basically the first fraction. 0.4 times 0.6 divided by 300, add. And then 0.45 times 0.55 divided by 200. And then finish your little bracket. Have you noticed that at least I don't need to worry about ordinary calculations? Pretty much if you do it from left to right, you're going to be fine. Now, when I hit enter, I get the answer 0.045 and some other digits. Are you comfortable about how we did that calculation? Right, so you got P1 guy in the story, a P2 guy. the sample size 1, the sample from size, the sample size 2. The difference is pretty easy, take them away from each other. The standard error is ugly, and that's this guy. And that might be the end of the question, right? So they might just ask you to find these two guys and move on. So that would be maybe question A, and that would be question B. But let's take it one more stage, one last step. Let's find confidence intervals. And we're going to use the empirical rule. Can you remember 1, 2, 3 standard deviations? As I call it, the 68, 95, 99.7 rule. 1, 2, or 3 standard deviations. And we're just going to focus on the 95% confidence interval. You're going to do P1 take away P2, because we want to do a confidence interval for the difference between the two, right? So this is your first number. Plus or minus, right, 2 standard errors. If it was a 99.7%, wouldn't I do 3 standard errors? And if it was a 68, wouldn't I just do 1 standard error, right? 1, 2, or 3. Now we know this guy, he is negative 0.05 plus or minus 2 times this guy. So it's going to be negative 0.05 plus or minus 0.09. And that's going to be, well, if you take it away, negative 0.14, and if you add it, 0.04. If you want to see what that would look like on a calculator, a negative uses this button down here. So you go negative 0.05, then you use that subtraction. Do you see they look slightly different? You see the negatives are slightly different look than the subtraction, 0.09, and that's this fella. And then negative 0.05, add 0.09, and you get that guy. And I like percentages, so that's negative 14% all the way up to 4%. And now we can answer this question. But you have to be really careful about how you answer it. Do you see that this interval contains negative and positive numbers? Right? If you imagine a little number line, negative 14 is about here, 13, 12, 11. And there's negative 10, 1, 2, 3, 4, 5. There's negative 5, 1, 2, 3, 4. There's 0, 1, 2, 3. And there's 4. And we are basically saying that the answer to the difference between those two groups is anywhere between here and here. And any one of those numbers, any one of those percentages could be the right answer. Do you notice that in this interval, 0 is in the interval? Right? So those two groups in our sample story, if I put my little guy here, the old and the young and do they like Pepsi, couldn't they be pretty much the same? Right. In this case, there's no evidence that they are different. That's not quite the same as saying that they're the same, but if there's no evidence that they're different, right, they could well be the same. So you might think, well, what would an interval look like if we wanted to prove that one was bigger or less than the other? Can you imagine an interval that was negative 14% to -5%. All these numbers are negative. Isn't that evidence that P1 is less than P2? Does that make sense? If P1 take away P2 is going to be negative, isn't that evidence? If you get an interval and it was all positive numbers, then that would be the first group is bigger than the second. If they're all negative, the first group is less than the second. If the interval contains 0, your statement's going to be that there are no evidence to suggest that they're different. So we tend to be evidence that the first guy is less than the second, evidence that the first guy is bigger than the second, and there is no evidence that they're different if 0 is in the interval. And that's your 3 conclusions that you can make once you've built one of these intervals together. Any questions about that process? Okay. That's basically all the start to finish, apart from some sentences, perhaps, about what does it mean. So let's look at some questions from the homework to see how they phrase them. Hopefully make it a little bit easier to see what's going on. Okay, let's see if I can make that bigger without losing words at the end. That was one too many. Okay. For each of the following situations, specify the mean of the sampling distribution of the difference in the sample means. God, that is more work than it's worth. We are only interested in the difference between the two groups. So 31% and 38%. You take the first guy to go first, take away the second guy to go second. And you notice that I've turned them into decimals because they don't want a percentage answer. Oh, almost put the wrong thing in there. Positive or negative and how much?
Negative 5.07.
And that's it. That's all you do. Right, so don't expect a lot at the beginning, right? We've kind of done the whole process start to finish. They're only doing a little bit. You might say, well, what about 400 people? Right? You notice I've mentioned 400 a couple of times. And be careful, let the first population be male and the second be female, because couldn't they be sneaky and give you the numbers back to front? So you have to remember to switch them. So I should check that I've done that one. This is female Democratic supporters. 31 male, 31 voted for the registered Democrat. First population is male. So this way was exactly the right one. But can you imagine they might have said down at the bottom here, let the first population be females and the second population be males. Now, if they did that, wouldn't you go the 38, take away the 31? That's about the only way you could be caught out, right? So make sure that you read the bit at the end so you know which number is first and which is second. Because the order that they write them down may not be the way that you're meant to use them, right? You might have to switch places. Now, here's a question where they're just asking us to do the standard error. A, B, and C, which one do you want me to do?
C.
C gets a job. Okay, I'm writing down the numbers I need to use, so let's see the story. The populations are left-handed and right-handed junior high school students. And they're interested in comparing the proportion that have learned to play musical instruments. Okay. Suppose that in truth, 45% of both have learned to play a musical instrument. A random sample, oh God, that's going to be an easy number. Won't P1 be 0.45? And won't P2 also be 0.45? Agreed? And the samples are 1,600 for right-handed and only 400 for left-handed. Okay. And we are going to get the standard error. So I'll return back. Now I've got all the numbers I think I need. And we'll see what we have. So the standard error for the difference is going to be the square root P1, 1 minus P1 hat over N1 added to P2 hat, 1 minus P2 hat over N2. That is going to be a 0.45 times a 0.55 over 400 people, plus a 0.45, a 0.55 out of 1,600 people. Then I go to the calculator and hopefully I don't screw up. Square root of 0.45 times 0.55 divided by 400, that's this one. Added to, it's going to be this one now. 0.45 times 0.55 divided by 1,600. And the answer I get to whatever they want, did they say how many decimal places? I can't see it unless it's at the top. Yep, 4 decimal places. So it's going to be 0.0278. And we are done. Are you comfortable with that question then? If you tell me P1 hat and P2 hat, you can find the difference. If you tell me P1 hat, P2 hat, and the sample sizes, can't you now get the standard error as well? Are we good? Okay. Now, can anybody remember the 10 rule? What was the 10 rule? It's a rule that allows you to say, yeah, you can do this stuff. What was it, Lauren?
I know it has to equal 10, but I can't remember the exact verbiage.
Okay, here it goes. You're right, it has to equal 10. All of these 4 things, every single one of these, has to be at least 10 or more, right? And as long as that is true, you are allowed to conduct the sampling distribution process. Now, when we did it last time, it was only for 1 sample, so you only needed to prove those 2 were bigger than or equal to 10. So let's take this one as our example, right? You tell me P1 is 0.45 and you tell me N1 is 400. So if you do that calculation, you're basically going to do 400 times that. And that ends up being the number of people who, I think this is playing violin or something, playing a musical instrument. And that ends up being 180. And if you do N1, 1 minus P1 hat, it's 400 times 0.55. And that ends up being the other 220. So they're okay. And if you do the second one, you've got P2 hat is also 0.45, but this time the sample is 1,600, and you do N1, P hat, N2, I should say, P hat 2, which ends up being 1,600 times that guy. That ends up being 720 people. That's definitely bigger than 1. And then you calculate that fella. So it's 1,600 times 0.55. And that happens to be 880. So if this story, the one about the left and right handedness, if we were checking Are we even allowed to do the analysis? The answer would be yes in this case, because every single one of those multiplications, right, these guys here, as long as the answer's 10 or bigger, you're allowed to do it. Suppose everything was great, but that last one, just for argument's sake, was 9, right? Different numbers. You wouldn't be able to do the analysis because that would fail under the size of sample, right? The 10 rule, which is basically a test on, is the sample big enough to do the process? And it's not just, 400 is big enough. It's a little bit more than that. And, the number of people who say yes has to be 10 or more, and the number of people who say no has to be 10 or more. So that's what the 10 rule is doing. Any questions about that? Okay. There's a big horrible question 3 that does exactly that. In fact, it does it 3 different times, so have fun. Okay, this is a version of question 4 now. I won't jump back and forward, there's too much going on here, so I'll read it to you. There is some evidence that women tend to vote early in the day and that men tend to vote later in the day. If men and women vote differently, then the exit polls taken early in the day may not affect the eventual results. I see where they're getting. You know how they do exit polls and they ask people who come out after they've voted and they say, who did you vote for? And they can get little snapshots. It gives them a way to predict what the final outcome might be. But what they're saying here is that women, they believe, tend to vote early in the day. So if you did a poll early in the day, wouldn't you get more women than men, essentially? And we know that women and men do vote differently, even if it's only a few %, they do vote differently. So you can see how that might cloud your prediction by a few percentage points, especially if it's a narrow race. Couldn't that make false predictions based on it because of it? So let's see what they managed to do to see if this is true. If men and women vote differently, we've mentioned that, right? Suppose that on a particular election, 52% of the voters who voted in the morning vote for candidate A. So in the morning, the percentage of people who voted for candidate A was 52. And then later in the day, we'll call it late, the percentage who voted was 49. So that might be a reflection of the women and the men voting, right? And in this story, it was 500 people in the morning that were asked, and it was 500 people in the late evening that was also asked. And we are now going to create from this all the different types of things that you would need. So let's do P1, take away P2. So that's 0.52, take away 0.49, and I get the answer 0.03. You agree? And standard error of P1 hat, take away P2 hat, is this big ugly formula. And so the standard error, also called the standard deviation, they keep changing its name, but it's the same thing, is 0.52 for this one, with a 0.48 over 500 plus 0.49, it's this guy, a 0.51, also 8500. And we are going to do the square root thing now. 52 times 48 divided by 500. Add 49 times 51 divided by 500. And the answer to 4 decimal places is 0.0316. Are we good so far? Right. Do I need anything else here? Oh, they did do, and I'm trying to get my, all I've done here right now is question B. What I didn't pay attention to was question A. But in question A, they only wanted you to do it for a single sample. So can you imagine that that fella would be 0.52 and that the standard error of just one guy, that would be this calculation here. So in question A, you're only going to do it for the first group. In question B, you do it for everybody else. And they have little pictures of it. I guess I should do a picture. The middle will be at 0.03, agreed? And then 1, 2, 3 standard deviations either side. So if we take this number and you keep adding it, this number here is 0.0616. This number here would be, yikes, 0.0932, and so on and so forth. Are we okay with that? One standard deviation, 2 standard deviations, 3, and then -1, -2, -3. The numbers are just downright ugly. That's the only issue I have. I don't know if I'm getting happy or sad faces here. Is it the fact that these decimals are so ugly that you're not sure where this is coming from? Are we okay? Okay, I'll assume it's just ugly numbers. But let's show you question 5 then, because it is very visual, and I think that might help. Can I make this any, oh, got somebody coming. Can I make this any bigger? That might help. Okay, researchers would like to know whether the proportion of elementary school children who are obese differ in rural compared to urban areas. So they get 700 kids from the urban area and 700 kids from the rural areas. And they compared the proportion who are obese. And we're going to define population 1 as elementary school children, essentially in cities, and population 2 is elementary school children, in rural areas, right? Defining words the parameter P1 represents. Well, P1 is essentially that group, isn't it? So you just pick the sentence that makes that one and make sure that it uses the word population. Why should it use the word population and not the word sample, which is what the next one's going to use? Where's the clue?
Parameter.
Yeah. Can you see it's a parameter? Second clue, less obvious. Do you notice there's no little funny hat above it? When you see P1 like that, it means it's a population parameter. If you see a little hat, even if they don't use the word sample, which they might not in some questions, it still means it's a sample, right? The little funny hat symbol that looks like that. So in this one, it would be the proportion of those who are sampled. It would be a base. And the proportion of population. Is it urban or rural? I should check that. P1 is urban, so I want it to be urban. So yeah, that's the right dots. Suppose that unknown to the researcher, P1 and P2 are actually the same number. Describe the sampling distribution. It's approximately normal with a mean of 0. Oh, and a standard deviation. Well, the standard deviation would depend on our sample size. That is a big calculation. Do you know my ugly square root guy? P1, 1 minus P1, that's the guy we're going to use. And won't we call P1 0.35 and P2 also 0.35? Okay, too much talking. I have to write this down. You can't keep it all in your head. No one could. In this story, you are told that this is 0.35 and that this is 0.35, and that in both cases, the sample sizes are the same and they're both 700. So you're being asked to find out what the standard deviation is, also called the standard error. Now, the only real difference in my formula is, do you notice that I'm using P instead of P hat? Right, it's essentially, if you tell me P hat, I'll use that. If you tell me P, I'll use that, right? You only get told one or the other. You don't typically get told both. So it's going to be 0.35 times 0.65 over 700. And to be really boring, won't this one be exactly the same numbers? 0.3, 0.65 over 700. No, I really want to do this calculation because they get a bit boring after a while. But 0.35 times 0.65 divided by 700, add the same thing again. And 0.0255 to 4 decimal places. Are we good with that? Right, now what would the picture look like? When you do a 0 in the middle and 1, 2, 3 standard deviations either side. So this one would be 0.0255. Then you would double that up to 0. I'm not going to do it in my head. 0.0255 times 2, which is 0.51, 0.051, and then you do it one more time, and you get 0.0765. Can you imagine one of the 4 pictures will look like that with these numbers, and you pick the one that looks like that? Are we okay with that question? You see there's basically a theme, isn't there? Find the difference, find the standard error, draw a picture. Right now, that's where the theme is going. Question 6 is basically the same story, but 900 kids instead of whatever it was, 700, and the P's are 20%. And 7 is the same question again, right? Question 8 is a little bit different. And what you're seeing here, I'm just copying it down, is a sample. And this guy's X, this guy's N, and this guy is called sample P. And this is in the year 2008, they had the sample. And this is an ongoing nationwide survey asked whether a respondent favours or opposes capital punishment, right? So should there be the death penalty? These, in 2008, 631 people out of 1932 said yes. And that's roughly what, 32, 33%. In 1993, 331 out of 1458, and that is 0.227. Where did these two decimals come from? I should do a check to make sure they're right. Where did these two decimals come from?
Dividing X by N.
Correct. So 631 divided by 1932 is to 3 decimal places, 327. So couldn't they have left that blank? And maybe they will do that in later questions. And you have to figure out what those are. But just like you said, how many people said yes out of the number? And they ask you to write these numbers down in question A. There's 2 boxes. So one of them is for that guy, and one of them is for that guy. And question B, they ask us to figure this thing out. Interesting notation. But I'm pretty sure I know what they mean. Would you agree they just want you to take this guy, take away that guy? So it's not P1, take away P2, but it's equivalent to it. So take that guy and subtract that guy. And the difference between those two, I believe, is 0.1. So what, 10% difference over that? What would that be? Over that 15-year period. So there's definitely been a change in opinion. Would you agree that the change in opinion seems to be in the direction of more people are in favor of the death penalty than used to be? It used to be this number in 1993, and now it's climbed up to that number. And finally, we get a 95% confidence interval question. So all the information we need is here. And we are going to find a 95% confidence interval, and we could do it from scratch, but actually the table has the answer, and it's written down like this. And it's written down like this because that's what computers do. And it's basically so all you needed to do was actually go to the table at the top and write down that. So somewhere between 17 and 13%. So our 95% confidence interval is that the difference between these two is somewhere in the range of 7 to 13%. Would you agree all of those numbers are positive? And if they're all positive, doesn't that mean that we now have evidence to prove that this guy is bigger than that guy? Because if you're positive, isn't the first guy bigger than the second guy? That makes sense? Now, if that interval had nothing but negative numbers, different story. But you imagine it was negative 15% to negative 13%, right? That could happen. Wouldn't that be evidence that the first guy is smaller than the second guy? In other words, less people are in favour of the death penalty, right, than used to be. And what do you do when your interval looks like this? What kind of sentence would you describe this interval as telling us? That interval is saying the first is bigger than the second. This interval is saying the first is less than the second. But what does this interval tell us? There's no evidence they are different. We're not saying that we know for sure that they're the same. Aren't we just saying there's no evidence to show that they're different? Couldn't it be a negative number, in which case the first one is smaller than the second? Couldn't it be a positive number, in which case the other is true? And put your last name